Alright, kiddos. Hope you guys had a good weekend. I know I did. Sorry I couldn't be here today. I've got a meeting here in the building all day, so if you get bored and want to see me, I'll be in the boardroom. Stop in and say hi today. But your job today is to start looking at 10.6. We're going to look at segment relationships in circles. The question we want to ask ourselves today is what relationships exist among the segments formed by two intersecting chords or among segments of two secants that intersect outside of a circle. We're also going to look at what happens when they intersect inside of stuff today. But I think if you pay attention to this today, I think this will be fairly simple. Skills that you're going to need to have to know is how to multiply and divide. I maintain if you can't do that, then you're in the wrong class. So again, what relationships exist among the segments formed by two intersecting chords or among segments of two secants that intersect outside a circle? So our goals today are to use segments of chords, tangents, and secants, all terms that we've talked about in the past. Okay? So the first term I want to start looking at here, segment of a chord. It says the segments formed from intersecting chords on the interior of a circle are called segments of a chord. If you notice right here, EA and EB right here and here are segments of chord AB, and DE and EC are segments of chord DC. Here's DE, here's EC. It forms that whole segment up there, okay? So there's going to be times where chords intersect on the interior of a circle. All right? We're going to start looking at some things for intersecting segments. One segment is going to be known as a tangent segment, highlighted in blue. It's a segment that is a tangent to a circle at an endpoint. So for instance, this segment right here can be outside here, but the endpoint has to stop right there and touch one point at the circle. And that's your tangent circle. Okay? Secant segment is a segment that contains a chord of a segment and has exactly one point on the outside of the circle. So if you look at PR right here, if you look at PR, we have the end point at R, and then one point of this segment is completely outside, and that point is P. So that's known as a secant segment. And then from that secant segment exists what's called an external segment. And the external segment is highlighted in red right here. Same setup as what's up here, but in red here from P to Q. P to Q is my external segment, okay? Up above, PR is my secant segment, and in the tangent segment, PS is your tangent segment. So definitions, I think there's some great illustrations in this column right here. I think that will guide you well throughout this. So with all of that said, let's get into the core today. What are we trying to accomplish? Okay. First thing we're going to look at is a theorem. This is called Segments of Chords theorem. This simply states if two chords intersect in the interior of a circle, if you notice over here, two chords intersect inside the circle at E, it says then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Right down here I've highlighted that EA times EB is equal to EC times ED. So really EA is right here. This segment times this segment, EA and EB is going to be equal to the other chord, two segment product ED times EC, and that's all that theorem states. So to give you an example down below here, we're going to use segments of chords theorem to solve this. It says find the length from A to B and P to Q. Okay? Well, what I do know is that I have two chords that intersect inside of a circle. So based on that theorem above, segments of chords theorem, we know that this segment right here, x, times this segment, x plus 6, I could say x squared plus 6x would have to equal the other product, since this intersects on the interior, x plus 1 times x plus 4. So here we go, kids. On the left, I've already done the distribution. X times x plus 6 is the x squared plus 6x. On the right side, we're going to have to FOIL. This will FOIL out to x squared plus 5x plus 4. Okay. If you notice on both sides, there's an x squared on both sides, so those simply cancel each other, meaning we have 6x equals 5x plus 4. If I subtract 5x from both sides, I have 1x equal to 4, implying x equals 4. So if I go back to what's asked here, find AB and PQ, well, guys, AB is defined as both distances here. In this case, I would plug 4 in for x. So AB, my friends, would equal 4 plus 6. That would make AB equal to 14. And then likewise, the other segment is P to Q. Again, I'm plugging 4 in for x, so I would have 4 plus 1 and 4 plus 4. The 4 plus 1 up here would be 5. The 4 plus 4 here would be 8. So PQ would have length 13. Right? So to answer the questions up here, AB again is 14. PQ is 13. Now as I'm recording this right here, I'm sitting here thinking to myself, if this is going too quickly, have the sub pause anytime you need to get stuff written down, but also feel free to pause it, read back, and make sure you understand stuff. If you're confused, help each other out. I want some good explanations amongst the groups today, all right? Okay, another theorem today. The one up above was called Segments of Chords theorem. This usually happens on the inside, and that's pretty easy, okay? Things are going to start to take a twist here a little bit. Okay, we're going to start looking at segments of secant theorems. Okay, secants are going to be these secant segments that start at E, go all the way up to B, but intersect at A, also go from E all the way over to D and intersect at C. Okay, secant segment says this. It says if you look at EA right here in red, and then times that by the whole segment E to B, that's equal to EC in red times that whole length of that segment, or that secant segment, ED. Okay? So I'll read this real quickly. If two secant segments share the same endpoint outside a circle, and again, the key word is outside, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. A lot of words, but what you really need to know is it's really this short segment right here, E to A, times the whole segment right here. That's going to equal this short segment outside times the whole segment right there. That's what this is all saying right down here. Okay? So example-wise on page 3, kids, here's what we need to look at, finding the value of x. If you notice right here, we have two secant segments. R runs through P and ends at Q. R runs through S, ends at T. What this is simply saying then is this distance R to P times the distance R to Q, that would be the whole segment, would equal the other secant segment outside of the circle, RS, times the whole secant segment, which is RT. So the values I'm simply going to plug in are the following. RP is 3, RQ is 9, RS is 4, and RT is kind of the tricky one. You've got to take that as 4 plus x. Okay? So it's the outside part times the whole part equal to the outside part of the circle times the whole part. Product of 3 and 9 is 27. I've got 27 equals 16 plus 4x. My north of Highway 3 math skills tell me that if I subtract 16, I have 11. That equals 4x. And all of you guys know that 11 divided by 4, even today, is still 2.75. Okay? So again, we're taking this short segment of 3 times the whole segment of, ooh, I screwed up. It's not 9, it's actually 12. I need to back up here. Hopefully you caught me. Yeah, we can't go 3 times 9, can we, kids? Good thing it's Monday. I can blame that excuse on that. 3 times 12 is what this should be. And that should equal 4 times 4 plus x. Okay, so this part right here, 3 times all of it, which is 12. So I've got 36 equals 16 plus 4x when I distribute. I've got 20 after you subtract 16 equals 4x. I like x equals 5 better. Okay, so now that I've confused you a little bit, make sure you understand the change that I made there. Okay, a lot of people just want to take 3 times 9. You can't do that. You got to understand this is all 3 plus 9, which is 12. Right? All right. Next theorem. Segments of secants and tangent theorems. If you notice right here, e to d, this here is a secant. Starts at E, hits the circle in 2 spots, C and D. However, EA in blue is a tangent segment. Starts at E, ends at A. Okay, formula for this is very much the same. Really just says EA squared. This tangent squared, tangent segment squared, is equal to the part that's outside, EC, so I'm going to call it the outside secant. Outside secant times the whole secant, which is ED. All right, now read this. It says if a secant segment and a tangent segment share an endpoint outside a circle, in this case E, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent, the blue line. So as I look at number 3, here's what I have. It says find W to X. Kids, W to X is simply my tangent one. Okay? So what we say here is X squared is going to equal the secant part, which is outside, 12 times the whole secant here of 27. Kids, 12 times 27 is 324, I believe. 270 and 54, yep, it's 324. And then if you punch in the square root of 324, you're going to get that x value to be 18. So to answer my question up here, find Wx. Well, Wx is defined by x, so Wx is going to equal 18 units long. So if you ever have a tangent right here, it's the tangent squared times the rules for the secant segment. Outside segment times whole segment. All right, last theorem here. Not really a theorem, it's a problem that we need to try and establish or understand. Really, it's right here. It says finding the radius of a circle. If I look at U to T, kids, is a tangent segment. And U to W is equal to, oops, I've got that written incorrectly. U to W is equal to a secant segment. So by our last theorem, I can simply say our tangent squared, which is 3, I can say 3 squared equals the outside secant of 1 times the whole secant, which is really 1r, 2r plus 1 more, so I could call this 2r plus 1. 3 squared, my friends, is 9. 1 times that quantity, 2r plus 1, is 2r plus 1. We simply two-step our way through this to find r now. I would have 8 equals 2r. So I would have 8 equal to 2r, in which case my radius is 4. And check it. If this radius is 4, and this is 4, it simply means that if I take my outside secant of 1 times my whole length right here of 9, I've got 9, and 3 squared right here is 9. Guys, not too much here today. What I'd ask you to do, if you're confused, go back and watch the examples again. You have everything up through your Chromebook, and what I'm going to ask you guys to do is to make sure you have the peer evaluations right here done for Tuesday when I come back and I'm in class with you. I'll also let you know that online book page online book page. 10.6 will be available to you today. So make sure you start looking at online book page 10.6. And kids, that won't be due until Wednesday. So if you can just look at your notes and pair up the examples, I think you should be in pretty good shape with this. All right, if you have questions, stop in and see me today. Otherwise, gosh, I think that this is pretty easy for you guys. You should do pretty well with it. So if you have questions, make sure you ask, but do the peer evaluations right now in your groups. Make sure you guys all agree. If you disagree, talk about why you disagree, and then you're probably going to have plenty of time to get started on the online pages, so make sure you do that. And then help my sub out if she or he has any questions regarding anything in the classroom. All right, you guys. This is weird teaching to an empty classroom, but you all rock. Keep up the good work, and I'll see you Tuesday.